Alright, so let's talk about orbital shapes. I've talked about the symmetry. Now let's actually relate this to something you can see on the sheet of paper. So what we're going to look at are the different values of angular momentum. So for L equals 0, we have 0 planar nodes. Now keep in mind, what a planar node does is that it divides up your electron density in terms of the XYZ Cartesian axis. So if we don't have any nodal planes, the electron density has to be symmetrically distributed across X, Y, and Z. And so an s-orbital, or L equals 0, is going to be a sphere. Easiest one to remember is S is sphere. What about when L equals 1? Well, we're going to have a plane, and the plane is going to divide the electron density into one half and the other. So for L equals 1, what we're going to have are two lobes of electron density. And we're going to have three of them, one oriented along X, Y, and Z. And so this is going to be the shape of your p orbitals. You're going to notice it because you see two lobes now, one for each side of that planar node. How about L equals 2? When L equals 2, we've got two planar nodes now, so we're dividing the electron density into 4 quadrants. And so when we're seeing a d-orbital, typically what we see are 4 lobes somehow in space. There is an exception to this, which will be the dz squared, which is basically looks like a p orbital with a donut around the base. But that really does actually have 2 planes associated. But typically what you're seeing with a d-type orbital are 4 distinct lobes in space. When we go to L equals 3, f orbitals, you're going to see 6 lobes oriented in space. Now again, there's going to be some exceptions because there are some weird ones where the planes are kind of curved. But what you're looking for with the f orbitals are 7 orbitals, each with 6 lobes associated with them. And this is going to be the shape you see here. And so these are the shapes you see for the different orbitals. When you actually solve the Schrodinger's wave equation, you actually see the shapes. Now, to give you kind of a note on the color code, you're going to see an alternating between red and green, black and white, whatever your book happens to do. So there's a couple things I want you to keep in mind with this. First of all, the shapes you're seeing are what are called isospheres. Basically, it's the chance of seeing an electron within that shape is at 90%. Electron density goes out to infinity. And so while we had these nice pictures of p and s orbitals, they're basically showing a cutoff point of 9%. In reality, they're not this well-defined hard sphere. It actually goes off infinitely. Just beyond that sphere, there's less than a 10% chance of finding it. The second thing is that the reason why we're seeing the color change is that actually the angular momentum is taking a different direction. So I told you before that, well, you might have some intuition with this. Angular momentum is like a spinning wheel. It's basically saying that on one side, the electron is spinning one way, and on the other side, the electron is spinning the other way. Now, we don't know whether it's clockwise or counterclockwise, but we just know it's on the opposite side. So that's kind of a fun fact with these nodes. Not only do they represent a region of 0 electron density, they also change the direction of the angular momentum as the electron is spinning. But that's why you'll see in these pictures, you see them constantly changing colors as they switch between the different planes, is that basically as the electron is on one side or the other, it's spinning in a different direction.